Hello friends. In our previous video, we were trying to understand the working of MOSFET, metal oxide semiconductor field effect transistor. Today, we will try to mathematically analyze it by deriving an expression for the drain current of MOSFET. We will also plot the drain characteristics and also the transfer characteristics. This video will help you to understand more about MOSFET. Let us try to find an equation for the drain current. Drain current means the current between drain and source. Current between drain and source. We are making use of few fundamental equations in order to get the drain current ID, which is the current between the drain and the source. Now, what is a current? Current I is equal to the rate of change of charge dq by dt, which can be approximated as the change in charge with time. In order to find the expression, we shall see how much charge is flowing from drain to source. We will find the charge Q. When the gate to source voltage VGS increases, inversion happens. If you remember, inversion happens. There will be electrons coming at the, because you know, if this is the N plus region and P is the substrate, on increasing the VGS, we will have electrons forming a channel between drain and source, and at a particular point, this channel, we have a channel at the area between source and drain. And we also know, by the virtue of the construction, there is a capacitor forming between the drain and the source. We have a metal gate, an oxide dielectric, and the semiconductor channel which forms the capacitor. If we just think about how the capacitor will be, we will be having a plate separated by dielectric, I will redraw it once again. We have one plate which is in this case made of the metal. The next plate is made of the semiconductor, and the gap between these two plates, which forms the capacitor, is the oxide. And also we know, if this is the capacitor, Q, charge stored in the capacitor, is equal to CV. Charge stored in the capacitor is CV. So we have Q is equal to CV and by the virtue of our knowledge, capacitance C is equal to the permittivity into area by the distance between the two plates. If that is the case, in case of MOSFET, we have the permittivity of the dielectric, which is the oxide permittivity epsilon OX, which is the oxide permittivity. Area is the width W into the length of the channel, area will be W into L and by the width of the oxide, which is the distance between the two plates. This is the capacitance into the voltage applied, which is VGS minus VT, where VGS is the gate to source voltage and VT is the threshold voltage. Here we are neglecting the VDS, effect of VDS. So this is the equation for the charge stored, and in order to find the current we need the time t, which is equal to length by velocity. So which is equal to the length L, the channel length, divided by velocity can be in terms of the charge will be mobility times the electric field, which is equal to L by mobility mu n into the electric field will be VDS by the length. On rearranging this, we will get L square by mu n VDS. This is the expression for time. Since the electric field is proportional to the voltage applied across the drain and source, which is VDS. Now, making use of these two expressions, we could write ID, which is equal to, just dividing these two expressions, this expression divided by this expression, we will get ID is equal to mu n, which is the mobility, epsilon OX by T OX, which is the permittivity of the oxide and thickness of oxide, into the width of the channel by length of the channel into VGS minus VT times VDS. This is the expression for the drain current, when we are considering the drain to source voltage VDS very small. Now, if we plot a graph between VDS and IDS, the drain to source current versus drain to source voltage. When VDS is small, we see that ID is linear by this expression. This can be, this is of the fashion ID is equal to G into VDS, where G is the conductivity, or this term as all forms the conductivity. This conductivity G increases with VGS. So, when we increase the gate to source voltage, the current also increases. If we decrease the gate to source voltage, current decreases. But it is linear. Now, if we increase the VDS, this was when VDS was very small. Now we will see what happens when VDS is increased. When VDS is increased, there will be a change in the equation of Q, which is CV, which is equal to epsilon OX by TOX into width into length. Earlier it was VGS minus VT. Now the factor, when VDS is increased, there is a factor of VDS which is half of VDS affecting the charge. Why we take half is because we are just considering the middle of the channel at this point. What is the voltage due to the applied VDS? So at the middle of the channel it will be half VDS. Here it will be half VDS. That effect is considered in writing this equation. The time t, as we had derived earlier, is equal to L square by mobility times the drain to source voltage. Now what happens? ID changes to mu n epsilon OX TOX W by L into VGS minus VT minus half VDS, the effect of the drain to source voltage in conductivity, times VDS. So the graph now becomes, there is a parabolic. Initially it was linear, now it becomes parabolic. This effect of VDS when considered our characteristics, the drain characteristics, from linear it has changed to the parabolic. Now at pinch off is at pinch off. Pinch off means VDS is equal to VGS minus VT. At that time,
another color, maybe the pink color. At pinch off, the channel shape which was parallel, it is like changing to this size, so that at a point there will be a pinch off. This is due to increase of VDS. The channel is shrinking at the drain side, and we have the normal channel at the source side. So in this case, in order to form this type of channel, VDS should be equal to VGS minus VT. Now if we apply this in our drain equation, we will have the ID or IDS, invariably we can call it as ID or IDS, is equal to mu n epsilon 0 x by T OX W by L VGS minus VT minus half VGS minus VT into VGS minus VT, since VDS is equal to VGS minus VT. So the expression for drain current becomes half mu n epsilon OX by T OX into W by L VGS minus VT plus VT all square, which means now the ID is independent of VDS, independent of VDS, so that our drain characteristics now flattens, because even if we increase VDS, it is not depending, the drain current is not depending, drain current is only now depending on the gate to source voltage. This is the drain characteristics of MOSFET. Now if we still keep on increasing VDS, the pinching off becomes more prominent, which causes early effect, because there is a slight increase which can be plotted back. If you remember the BJT, we have an early voltage. So the drain characteristics is this. For a particular VGS, initially we have a linear portion. In between, when VDS is increased, it becomes parabolic, and at pinch off it flattens. It doesn't depend on VDS. So this explains the drain current and the drain characteristics of the MOSFET. And the figure shows the drain characteristics of the MOSFET, which is a relationship between, the graph is drawn between ID, which is the drain current, and VDS, which is the drain to source voltage. Actually, when VDS is increased, the drain current ID should increase, but due to the applied VGS,
the drain current is controlled at certain level, and that is why the drain characteristics have this shape. Another characteristics of interest would be the transfer characteristics. The transfer characteristics define the change in the value of VDS with the change in ID and VGS in both depletion and enhancement mode. The figure shows the transfer characteristics of drain current versus gate to source voltage. In the x-axis, it is not VDS, it is VGS. So this is the relationship between the drain current and the VGS. So these two characteristics, these two graphs will help us to understand more about MOSFET. Thank you.